Ferromagnetism is the basic mechanism by which certain materials, such as iron, form permanent magnets, or are attracted to magnets. In physics, several different types of magnetism are distinguished. Ferromagnetism, including ferrimagnetism, is the strongest type. It is the only one that typically creates forces strong enough to be felt, and is responsible for the common phenomena of magnetism in magnets encountered in everyday life. Substances respond weakly to magnetic fields with three other types of magnetism: paramagnetism, diamagnetism, and anti-ferromagnetism, but the forces are usually so weak that they can only be detected by sensitive instruments in a laboratory. An everyday example of ferromagnetism is a refrigerator magnet used to hold notes on a refrigerator door. The attraction between a magnet and ferromagnetic material is the quality of magnetism first apparent to the ancient world, and to us today. Permanent magnets, materials that can be magnetized by an external magnetic field and remain magnetized after the external field is removed, are either ferromagnetic or ferrimagnetic, as are the materials that are noticeably attracted to them. Only a few substances are ferromagnetic. The common ones are iron, nickel, cobalt, and most of their alloys, and some compounds of rare earth metals. Ferromagnetism is very important in industry and modern technology, and is the basis for many electrical and electromechanical devices such as electromagnets, electric motors, generators, transformers, and magnetic storage such as tape recorders, and hard disks, and non-destructive testing of ferrous materials. History and distinction from ferrimagnetism. Historically, the term ferromagnetism was used for any material that could exhibit spontaneous magnetization, a net magnetic moment in the absence of an external magnetic field. This general definition is still in common use. More recently, however, different classes of spontaneous magnetization have been identified when there is more than one magnetic ion per primitive cell of the material, leading to a stricter definition of ferromagnetism that is often used to distinguish it from ferrimagnetism. In particular, a material is ferromagnetic in this narrower sense only if all of its magnetic ions add a positive contribution to the net magnetization. If some of the magnetic ions subtract from the net magnetization, if they are partially anti-aligned, then the material is ferrimagnetic. If the moments of the aligned and anti-aligned ions balance completely so as to have zero net magnetization, despite the magnetic ordering, then it is an anti-ferromagnet. These alignment effects only occur at temperatures below a certain critical temperature, called the Curie temperature, for ferromagnets and ferrimagnets, or the Néel temperature, for anti-ferromagnets. Ferromagnetic materials. The table on the right lists a selection of ferromagnetic and ferrimagnetic compounds, along with the temperature above which they cease to exhibit spontaneous magnetization. See Curie temperature. Ferromagnetism is a property not just of the chemical makeup of a material, but of its crystalline structure and microstructure. There are ferromagnetic metal alloys whose constituents are not themselves ferromagnetic, called Heusler alloys, named after Fritz Heusler. Conversely, there are non-magnetic alloys, such as types of stainless steel, composed almost exclusively of ferromagnetic metals. Amorphous, non-crystalline, ferromagnetic metallic alloys can be made by very rapid quenching, cooling, of a liquid alloy. These have the advantage that their properties are nearly isotropic, not aligned along a crystal axis. This results in low coercivity, low hysteresis loss, high permeability, and high electrical resistivity. One such typical material is a transition metal-metalloid alloy, made from about 80% transition metal, usually Fe, Co, or Ni, and a metalloid component, B, C, Si, P, or Al, that lowers the melting point. A relatively new class of exceptionally strong ferromagnetic materials are the rare earth magnets. They contain lanthanide elements that are known for their ability to carry large magnetic moments in well-localized f orbitals. Actinide ferromagnets. A number of actinide compounds are ferromagnets at room temperature or exhibit ferromagnetism upon cooling. PUP is a paramagnet with cubic symmetry at room temperature, but which undergoes a structural transition into a tetragonal state with ferromagnetic order when cooled below its Tc equals 125 K. In its ferromagnetic state, PUP's z-axis is in the 100 direction. In NPFE2 the z-axis is 111. Above Tc 500 K NPFE2 is also paramagnetic and cubic. Cooling below the Curie temperature produces a rhombohedral distortion wherein the rhombohedral angle changes from 60 degrees, cubic phase, to 60.53 degrees. An alternate description of this distortion is to consider the length c along the unique trigonal axis, after the distortion has begun, and a as the distance in the plane perpendicular to c. In the cubic phase this reduces to c/a equals 1.00. Lithium gas. In 2009, a team of MIT physicists demonstrated that a lithium gas cooled to less than 1 Kelvin can exhibit ferromagnetism. The team cooled fermionic lithium-6 to less than 150 Nk, 150 billionths of 1 Kelvin, using infrared laser cooling. This demonstration is the first time that ferromagnetism has been demonstrated in a gas. Explanation. The Bohr Van Leeuwen theorem, discovered in the 1910s, showed that classical physics theories are unable to account for any form of magnetism, including ferromagnetism. Magnetism is now regarded as a purely quantum mechanical effect. Ferromagnetism arises due to two effects from quantum mechanics: spin and the Pauli exclusion principle. Origin of magnetism. One of the fundamental properties of an electron, besides that it carries charge, is that it has a magnetic dipole moment, i.e., it behaves like a tiny magnet, producing a magnetic field. This dipole moment comes from the more fundamental property of the electron that it has quantum mechanical spin. Due to its quantum nature, the spin of the electron can be in one of only two states, with the magnetic field either pointing up or down, for any choice of up and down. The spin of the electrons in atoms is the main source of ferromagnetism, although there is also a contribution from the orbital angular momentum of the electron about the nucleus. When these magnetic dipoles in a piece of matter are aligned, point in the same direction, their individually tiny magnetic fields add together to create a much larger macroscopic field. However, materials made of atoms with filled electron shells have a total dipole moment of 0, because the electrons all exist in pairs with opposite spin. Every electron's magnetic moment is cancelled by the opposite moment of the second electron in the pair. Only atoms with partially filled shells, i.e., unpaired spins, can have a net magnetic moment, so ferromagnetism only occurs in materials with partially filled shells. Because of Hund's rules, the first few electrons in a shell tend to have the same spin, thereby increasing the total dipole moment. These unpaired dipoles, often called simply spins even though they also generally include angular momentum, tend to align in parallel to an external magnetic field, an effect called paramagnetism. Ferromagnetism involves an additional phenomenon, however. In a few substances the dipoles tend to align spontaneously, giving rise to a spontaneous magnetization, even when there is no applied field. Exchange interaction. When two nearby atoms have unpaired electrons, whether the electron spins are parallel or antiparallel affects whether the electrons can share the same orbit as a result of the quantum mechanical effect called the exchange interaction. This in turn affects the electron location and the Coulomb, electrostatic, interaction and thus the energy difference between these states. The exchange interaction is related to the Pauli exclusion principle, which says that two electrons with the same spin cannot also be in the same spatial state, orbital. This is a consequence of the spin statistics theorem and that electrons are fermions. Therefore, under certain conditions, when the orbitals of the unpaired outer valence electrons from adjacent atoms overlap, the distributions of their electric charge in space are farther apart when the electrons have parallel spins than when they have opposite spins. This reduces the electrostatic energy of the electrons when their spins are parallel compared to their energy when the spins are anti-parallel, so the parallel spin state is more stable. In simple terms, the electrons, which repel one another, can move further apart by aligning their spins, so the spins of these electrons tend to line up. This difference in energy is called the exchange energy. This energy difference can be orders of magnitude larger than the energy differences associated with the magnetic dipole-dipole interaction due to dipole orientation, which tends to align the dipoles antiparallel. In certain doped semiconductor oxides, RKKY interactions have been shown to bring about periodic longer-range magnetic interactions, a phenomenon of significance in the study of spintronic materials. The materials in which the exchange interaction is much stronger than the competing dipole-dipole interaction are frequently called magnetic materials. For instance, in iron, Fe, the exchange force is about 1,000 times stronger than the dipole interaction. Therefore, below the Curie temperature, virtually all of the dipoles in a ferromagnetic material will be aligned. In addition to ferromagnetism, the exchange interaction is also responsible for the other types of spontaneous ordering of atomic magnetic moments occurring in magnetic solids, antiferromagnetism, and ferrimagnetism. There are different exchange interaction mechanisms which create the magnetism in different ferromagnetic, ferrimagnetic, and antiferromagnetic substances. These mechanisms include direct exchange, RKKY exchange, double exchange, and super exchange. Magnetic anisotropy. Although the exchange interaction keeps spins aligned, it does not align them in a particular direction. Without magnetic anisotropy, the spins in a magnet randomly change direction in response to thermal fluctuations and the magnet is superparamagnetic. There are several kinds of magnetic anisotropy, the most common of which is magnetocrystalline anisotropy. This is a dependence of the energy on the direction of magnetization relative to the crystallographic lattice. Another common source of anisotropy, inverse magnetostriction, is induced by internal strains. Single-domain magnets also can have a shape anisotropy due to the magnetostatic effects of the particle shape. As the temperature of a magnet increases, the anisotropy tends to decrease, and there is often a blocking temperature at which a transition to superparamagnetism occurs. Magnetic domains. The above would seem to suggest that every piece of ferromagnetic material should have a strong magnetic field, since all the spins are aligned. Yet iron and other ferromagnets are often found in an unmagnetized state. The reason for this is that a bulk piece of ferromagnetic material is divided into tiny regions called magnetic domains, also known as Weiss domains. Within each domain, the spins are aligned, but, if the bulk material is in its lowest energy configuration, i.e. unmagnetized, the spins of separate domains point in different directions and their magnetic fields cancel out, so the object has no net large-scale magnetic field. Ferromagnetic materials spontaneously divide into magnetic domains because the exchange interaction is a short-range force, so over long distances of many atoms the tendency of the magnetic dipoles to reduce their energy by orienting in opposite directions wins out. If all the dipoles in a piece of ferromagnetic material are aligned parallel, it creates a large magnetic field extending into the space around it. This contains a lot of magnetostatic energy. The material can reduce this energy by splitting into many domains pointing in different directions, so the magnetic field is confined to small local fields in the material, reducing the volume of the field. The domains are separated by thin domain walls a number of molecules thick, in which the direction of magnetization of the dipoles rotates smoothly from one domain's direction to the other. Magnetized materials. Thus, a piece of iron in its lowest energy state, unmagnetized, generally has little or no net magnetic field. However, the magnetic domains in a material are not fixed in place, they are simply regions where the spins of the electrons have aligned spontaneously due to their magnetic fields, and thus can be altered by an external magnetic field. If a strong enough external magnetic field is applied to the material, the domain walls will move by the process of the spins of the electrons in atoms near the wall in one domain turning under the influence of the external field to face in the same direction as the electrons in the other domain, thus reorienting the domains so more of the dipoles are aligned with the external field. The domains will remain aligned when the external field is removed, creating a magnetic field of their own extending into the space around the material, thus creating a permanent magnet. The domains do not go back to their original minimum energy configuration when the field is removed because the domain walls tend to become pinned or snagged on defects in the crystal lattice, preserving their parallel orientation. This is shown by the Barkhausen effect. As the magnetizing field is changed, the magnetization changes in thousands of tiny discontinuous jumps as the domain walls suddenly snap past defects. This magnetization as a function of the external field is described by a hysteresis curve. Although this state of aligned domains found in a piece of magnetized ferromagnetic material is not a minimal energy configuration, it is metastable, and can persist for long periods, as shown by samples of magnetite from the sea floor which have maintained their magnetization for millions of years. Heating and then cooling, annealing, a magnetized material, subjecting it to vibration by hammering it, or applying a rapidly oscillating magnetic field from a degaussing coil tends to release the domain walls from their pinned state, and the domain boundaries tend to move back to a lower energy configuration with less external magnetic field, thus demagnetizing the material. Commercial magnets are made of hard ferromagnetic or ferrimagnetic materials with very large magnetic anisotropy such as alnico and ferrites, which have a very strong tendency for the magnetization to be pointed along one axis of the crystal, the easy axis. During manufacture, the materials are subjected to various metallurgical processes in a powerful magnetic field, which aligns the crystal grains so their easy axes of magnetization all point in the same direction. Thus the magnetization, and the resulting magnetic field, is built into the crystal structure of the material, making it very difficult to demagnetize. Curie temperature. As the temperature increases, thermal motion, or entropy, competes with the ferromagnetic tendency for dipoles to align. When the temperature rises beyond a certain point, called the Curie temperature, there is a second-order phase transition and the system can no longer maintain a spontaneous magnetization, so its ability to be magnetized or attracted to a magnet disappears, although it still responds paramagnetically to an external field. Below that temperature, there is a spontaneous symmetry breaking and magnetic moments become aligned with their neighbors. The Curie temperature itself is a critical point, where the magnetic susceptibility is theoretically infinite and, although there is no net magnetization, domain-like spin correlations fluctuate at all length scales. The study of ferromagnetic phase transitions, especially via the simplified Ising spin model, had an important impact on the development of statistical physics. There, it was first clearly shown that mean field theory approaches failed to predict the correct behavior at the critical point, which was found to fall under a universality class that includes many other systems, such as liquid-gas transitions, and had to be replaced by renormalization group theory.
Please subscribe and thanks for watching.